So this is in a there is a PID. So sorry, this is not transfer function. So in here in a PID. So G note is PID. In PID, the control constant gains are like this: KP, KD, and KI. So here is a feedback. So the feedback gain feed feedback. So feedback is just G plus just say G times G O times G O with G naught, comma the constant feedback loop. So the feedback loop is H, and so there is D my M, and the next algorithm is just here. I have, by the way, we have to understand about the point is what I mentioned in here. So this is a plant dynamics. So this is a plant dynamics, which is a series of a mathematical equation. So finally, which is represented in a transfer function, and here is the constant sensor unit or the feedback gain. Here is the plant without control, and here the step response what you see. So here I'm gonna represent the insert the control algorithm or the control variable. So KP, KI, KD, and here the G note is the controller. Values are like KP, KD, and KI. So M is the feedback of G times G naught. So G is in the plant without controller, and GO is the plant without with controller. So from here, the transfer of, like, let's say transfer function, not transfer, the step response. So the step response of the step response of M, the step response of M is, now we will see the step response of M. So here are my step response. So here is a run. So click and single click and run, and so the continuous function of graph with controller. There is the controller portion, and this is the non-controller portion. This is a plant dynamics where I mentioned the vehicle before controller and the vehicle will be after controller. So there is a normal equation which is manipulated manually, and here are the controller algorithms are basically in order to regulate, in order to control, in order to govern the certain the mechanics of the entire system. So we'll see about the visual effect in here. So there is the graph with the function. So we'll see from here again. This is the time in second is now with controller and without controller. So in here I will share you about the KP values. Here my K value, by the way, grid on. So here let's make a grid. So let's grid. So because the graph is with name without grid, so grid on. So grid on, and here also let's just grid on. So I wanted to grid on here. So run. So before I'm gonna insert the grid, there is no vertical guiding lines in here. Look in the graph, in the simulation values in graph, no grid is a vertical grid and horizontal grid is, except the representing time is amplitude versus second here. Now I will run the dedication when I insert the grid on. So here run. So we'll see the visual effect in a graph here. So it is the grid. So this is a vertical grid, by the way here. So now there is M, and there is by the way the time in second. The algorithm function is inserted in order to modify the graph. The time simulation in second is also increased. So here the amplitude here. So now let's show you about the KP value. So there is a gain we're gonna regulate. So in order to regulate, in order to increase up and down the gain, so let me show you. So the KP value is, let's say press select, highlight the KP value, and then right click and then increment the value and run section. So here this symbol or this adjuster is displayed. So this is an adjuster in order to increase, in order to multiply, in order to divide, in order to subtract. So we will adjust the values in here. So my value is now kp is equals to 1. Let's make kp is 2. So we'll see the graph before kp, and kp is equals to 2. So there is a value kp is equals to 2. Let me reduce again. So let's minimize, and so which is 1. So we'll look the graph function here. So there is the kp values. Kp value is the constant, proportional constant is in here. So the kp value is increase. So now the kp value is now increased. So the graph function represented in here is also nearest to the settling time here. So from here, let me mention, let me tell you, let me show you about one critical thing here. So here, this is a grid. So hold on, this is a grid one. So grid is already present. So hold on. So hold on means the adjuster value will not be shifted. So to do that, let me press. Here is not necessary. So hold on. So save my function here, save. So here save. So hold on. So let me make 1 again, and so we'll see the effect. So now save, run. So there is the amplitude. So here, so there is the pressed function. So k is equals to 1 and k is equals to 3. So let's add again. So the kp value is let's say it is incremental section. So let's add again. So the adjusting parameter is increased and increased. So the value is also here. This is the values which are increased and increased. So let me reduce back. So here are the response graph. So the step responses are tends to back here. So let me show. Let me reduce here. Reduce. So you will see the effect here. So let's reduce again. Reduce, so which is 1. So the graph is only with 1. So look here. So now this is the adjuster, by the way, in order to regulate the kp values in here, which is now -1. So there is a negative value, by the way, which is a continuous time transfer function. And the next thing I would like to show you is we have to know there is the negative value. So look, it is in the negative region because it is -1. So let's make into a positive 0. So 1, 2, sorry. So now it is up to 3. So the kp1, kp2, kp3. So we'll see the graph effect in here. Okay, wait, because it was simulating the function. The kp value is tends to the effect is now at the -0 region, so which is a -1 region. The step response is the negative region. So there is, by the way, the mechanism we are representing the transfer function of this k controller. So the Zato controller is the PID, so the P gain, the I gain, the PD gain, and PI gain. So the gain schedules are represented in such a way. So in here, it takes a